Okay, now, so we should more or less ready to start. For those who are listening now, I welcome you to this today's seminar, which is, I think, the number nine minimum seminar series. The purpose of this seminar series is actually to provide a basis, for tutorial lectures for our researchers and students to learn about lunar science. It seems that our National Space Agency is planning a lunar mission, and however there are not that many how to say planetary scientists, lunar scientists in Taiwan. So I think that we need to do that in a hurry. Anyway, so we have already more or less like 40, 50 lectures. You could find them on our webpage. And today we're very happy to have a Jamey Szalay, who, as you can see here, is a young scientist. So will be our hope in our future. And he's now currently in Princeton, working in the astrophysical, plasma lab, right? I used to tell people more about that. But then he originally graduated from University of Colorado Boulder, and he was a student of Professor Mihaly Holany. And I remember that you were working on this student Dusk experiment, right? And then going all the way from the Earth to what, 50 AU, 40 AU, and counting only one dust. And you wrote a paper, many people about it. So I think that tells you that that Jamey, he for some, I think he went to the Southwest, right? Am I right? That's San Antonio, and for 1.5 years as a postdoctoral research scientist. Then he now has migrated to New Jersey to work in the new solar, I would say, space physics lab of a space physics group of Princeton, and and today his talk is only one of the I would say one of the 10 things he's working on, and so we are going to hear from him plenty of times in future. Okay, Jamey, go take it away.
All right, so yeah, thank you for inviting me to give this talk. I wish we were all in person in Taiwan, perhaps, and we could meet and interface in person. But in lieu of that, it's nice that we're able to meet like this and have people from around the community join. So again, thank you. I'm really looking forward to sharing some of our work at the Lunar Ejecta cloud. This is something that I worked on in graduate school, and it's been a passion of mine since then. And there's been a lot of very exciting results that have come out of what was a pretty small mission, and there's a lot of room to make even more exciting discoveries in the future. So just a brief introduction, Dusk, which I think many of you have heard about before, but it makes up plasma is 99% of the visible matter in the universe, and a large fraction of this is dusty. And so dust phenomena occur throughout the solar system in planetary formation and nebula and in planetary rings, cometary activity, noctilucent clouds in our atmosphere, and even in thunderstorms and volcanoes. It's everywhere and has all kinds of interesting phenomena throughout the universe. Within our solar system, there's a zodiacal cloud that's mainly the most dense, kind of near the orbits of all the planets, and that's sourced by interplanetary dust particles that come from asteroids, moons of other airless moons of planets, and a variety of comets that are either long period, short period, or even Kuiper belt objects. We also have discovered by Ulysses a population of interstellar material that's flowing through our solar system that we will not discuss further, but is interesting in its own respect. So all of that material in interplanetary space, when Earth passes through it with its atmosphere, that material ablates and burns up and produces these brilliant shooting stars that we all like to see at night. And that same material is also incident on the lunar surface. And unlike Earth, which has an atmosphere, the surface of the moon is not protected by any any atmosphere, and so everything that's incident on it hits the surface and creates impact ejecta plumes. And those processes sustain permanently present and very interesting impact ejecta cloud at the moon that was discovered by Laddie and will be the focus of today's discussion and talk. And I forgot to mention, please feel free, don't hesitate to interrupt if you have any questions. I understand that this is a tutorial and this should be informal, so again, please don't hesitate to interrupt. So the meteoroid population hitting the moon, we like to break it into kind of two separate groupings. There's meteor showers, which are when material has come off of some parent body and it has orbits that dynamically decouple from the parent but are in similar orbits to its parent orbit. And so on the left here, for example, that's the Geminid stream in some representation. And if Earth or the moon happens to pass through that tube of material, you get a meteor shower or a meteoroid shower if you're an airless planet or body. Now, over time, the grains in those very discrete tubes will decouple from their parents completely and be randomized and incorporated into the average sporadic background. But even that background is not isotropic, that has directionality. And so this is kind of one of the earlier images showing that there's multiple sources. And so the sporadic background is comprised of a variety of sources that we just mentioned. So, for example, in the top right, is the asteroidal source. And so we think in total there's about 43 tons per day that impact Earth. A small fraction, about 10% of that, we think are from asteroids, and they impact us in this frame. So this is a mole-wide projection of the entire sky. This is like a windshield view. So the center is the apex direction, the direction of orbital motion. And to the left, 90 degrees, is the direction of the sun. So that's like if you're in the driver's seat at Earth and you look out the left window, there's the sun. And so in the top right, you can see the asteroidal sources. They actually impact us slow, and they kind of this narrow ring of impactors. We have long period comets on the bottom. They comprise the apex source. They're actually in retrograde orbits, flowing against the traffic, if you will. Then there's a northern and toroidal source. Those are from high inclination orbits that impact us near the poles. And the most prominent source of interplanetary dust impacting the Earth-Moon system is from Jupiter family comets, and that's about 80% of the material and mass that we think is impacting, and that is primarily in a what we call the Helian and anti-Helian source, just due to the nature of the orbits, the vector addition of their orbits and Earth's or the Moon's has them impacting us from nearly the sun direction or nearly the anti-sun direction, and so you have the Helian and the anti-Helian. So these variety of sources comprise, in the center, this is the sum of them all, the average sporadic background. And that is incident on Earth. It's had a long history of radar measurements, and that very same impactor population is hitting the moon. So how do we measure that? So we had a mission called Laddie. It was a small NASA mission directed that had 3 separate instruments and a laser communication demo. And one of them is the Lunar Dust Experiment, LDEX, which is an impact ionization dust detector. The way it works is you get an impact that hits the surface of the moon, it ejects grains up into space, and then we kind of scoop it up, so to speak. When we fly through, we have this hemispherical target, and a dust grain impacts that target. If it hits it over about 1 kilometer per sec, it impact ionizes. And then we have an electric field set up that take the electrons and they get absorbed into the target, and the ions get accelerated through some grids and into a microchannel plate that then they're amplified, and that's our cleanest signal. And so we get a separate ion and electric signal for grains above a certain size. So for example, here's one waveform. They're showing on the top, this is the microchannel plate, the ion signal. You can see it's a lot cleaner than what's shown on the bottom, which is the electron signal. And so we can get double coincidence measurements like this, 2 waveforms, for any grain above about 0.7 microns in radius, and we can detect just the ion portion down to about 0.3 microns in radius. So the Laddie mission orbited the moon for about 6 months. It had an initial high altitude phase that's at this top ring. This is not to scale, but it shows you the altitude distribution and the time we spent observing. So for a few weeks, we were in this high altitude, mostly circular orbit at about 240 kilometers. And then we pumped down for a couple weeks, and then we got into this a little more eccentric orbit that kind of peaked around 50 kilometers above the Dawn lunar terminator. And this is the entirety of the LDEX dataset in some representation. This is a daily average smoothed impact rate for 2 different size thresholds. The top is the more abundant, smaller grains that we could detect with a single, just the ion channel. And the bottom shows the impact rate from when we could detect both the ion and electron channel. And you can see that there's variability over time on many different timescales. There's daily timescales, there's monthly timescales, and then there are sporadic inputs. For example, the Geminids lit us up even an average impact rate a factor of 3, but when you look at it at that specific hemisphere of the moon, for example, it was even larger. And so the moon was very responsive and receptive to changes in the interplanetary meteoroid flux, and there's all kinds of interesting science and physics that you can do with that sensitivity. So we take all the impacts, and with a few assumptions, we can convert impact rate into density distribution. And this is now the density distribution that we observed throughout the entire mission of the Lunar Impact Ejecta Cloud. And there's a couple features of note here. There's a couple asymmetries that we found. First, there's a dawn-dusk asymmetry. So in this frame, the sun is to the left, and dawn is in the upward, and same with the orbital motion. It's in the upward direction. And you can see that there's a significant more, about a factor of 5 to 10, density at the dawn hemisphere compared to dusk. There's also another asymmetry that it's slightly, the peak density is slightly canted towards the sun. And so those 2 features were something that we explored in trying to understand the impactor distribution to the moon. And the way that we did that, was we took those very same sources we just discussed and asked, well, can we make some combination of those and put them together to explain the pattern that we see here? And so that's what we did. And very early on, after getting all the data down, we were able to explain it by the Ejecta cloud initially with 3 separate sources. And so we had a helion, an antihelion, and an apex source. The helion and antihelion, shown in blue and red, are all part of the same population of bound grains, likely from Jupiter family comets, that they have an eccentricity that's larger than Earth's, and they cross Earth's orbit. And so when they're on their outbound part of their trajectory, they form the helion source in blue. And when they're on the inbound, they form the antihelion source. And for some reason, we required more helion source. There seemed to be more ejecta produced from the sunward direction than the nighttime. Additionally, it turned out that the #1 primary culprit of producing impact ejecta at the moon was actually a lower flux population of very high-speed grains forming the apex source. And these are from long-period comets, Halley type and Oort cloud. And so these go backwards, so to speak. They go against traffic. They hit you at about 60 kilometers per second. So you don't need as many of them to produce a large amount of impact ejecta. And so this is that view now in another representation. This shows those 3 sources. We add them together. Given the best understanding of what the surface response is, we use a cosine cubed based on experimental data. You get 1 cosine just from the area projection and a cosine squared from the experiment. And so in gray here is our averaged density by local time. And then here are these 3 sources again, and then the white line is the sum of them. And you can see that it reasonably well reproduces the structure given these 3 sources. And we initially attributed that there might be just more grains impacting from the helion direction than the antihelion. And we'll come back to that later. So in addition to that average structure, we saw a synodic modulation of the lunar ejecta cloud. So as the moon moves around the Earth, plus or minus 1 kilometer per sec, its orbital speed relative to the Earth, we get an enhancement as the moon is moving kind of towards all these sources on the top right quadrant. You get an enhancement of the impact ejecta cloud. It kind of grows, and then as the moon moves through its orbit and runs away from these various impactor sources, then it shrinks. And so there's a very predictable response that we saw. The moon responds to the changes, very small changes in speed, and then flux to its impactor populations. We also measured an annual variation. Unfortunately, we only had 6 months, and then the first 2 months were dominated by meteor streams. And so with about 4 months of data, we showed a trend that showed it looked like the ejecta cloud cant angle kind of went from more sunward in January to almost symmetric in April. And so there was some annual trend. We would have loved to see a year's worth of data, but this is still very excellent and exciting. And lastly, in altitude, there was a clear trend. So on the left is if you take all of our data and just show it as a function of altitude, and there's some very strange structure to that you might see initially, but we didn't observe every altitude and local time. There was a bias and a convolution between those two, and so it turns out if you pick apart just isolating local times, so for example, the dawn terminator, where we got the most best statistics because we spent the most time, it was the most dense. That's shown here on the right, and it turned out that the altitude distribution for the lunar ejecta cloud very well fit an exponential with a scale height of about 200 kilometers. And this was actually counter to expectations from the Galileo era when we flew by the icy satellites, the Galilean moons, and found that it was well represented by a power law. And so the speed distribution that we get out of that is also very different, and that power law on altitude was born from the very reasonable assumption that impact ejecta forms a power law, where the smaller the speed, the more impact ejecta. The problem with that is you have to introduce an artificial cutoff, because otherwise you have an infinite amount of grains at zero velocity, and so there is some artificiality to such an assumption, where what we found, but it very well reproduced the data, and likely that's due to the fact that Galileo was a lot farther with respect to the planetary radii, the radii of each moon. It was farther away than we were with LADI, and so we were maybe just probing a different regime in physics. So the red curve here shows what we would have expected with the Galileo distribution, speed distribution, and the green shows what we actually got, and this is inverting with conservation of energy, inverting the density distribution into a speed distribution. And we got a very pleasant, nice Gaussian shape. This is simply inverting an exponential scale height with conservation of energy. And you get this where you have a very reasonable 0 at 0. It has kind of this Gaussian-esque peak somewhere, and then it tails off to 0 again at high speeds. And this speed distribution very well reproduced and represented the data. So we take all of that together, and we're able to form an analytic expression, an approximation of the impact ejecta cloud at the moon. And so what we did is we said, okay, it was an exponential in altitude. You can see, I'll just walk through each term. So the density is a function of local time, altitude, and size. It's an exponential in altitude. It's a power law in size. And then it's the sum of a bunch of cosine cubes multiplied by a heavy side function, so you don't go past 90 degrees on either side. And the variety, however many sources that you have. In this case, this was 4 sources: the helion, anti-helion, the apex, and then a very small contribution in the backside, the anti-apex. And so we put together this average cloud distribution that we can then leverage and use for predictions and understanding and calculating gardening rates and a lot of other things. But one of the mysteries still remained, which is why we still, in this approximation, we treated the moon as on average symmetric about the about the dawn-dusk terminator. And that's because we thought that maybe we just caught, for some amount of time, an asymmetry in the helion-anti-helion source, and maybe if we had waited another 6 months, it would have flipped the other way, because there's no real a priori reason to expect that you shouldn't have more grains always going away from the sun on bound orbits than you have coming back. And so on average, you would expect that there should be equal fluxes from helion and anti-helion. But we actually, last year, were inspired by measurements from Parker Solar Probe. So that mission is the closest thing we've ever sent to the sun. It does not have a dedicated dust detector, but dust is maybe one of the most popular words in the mission right now, or unpopular, it depends on who you ask, because it is sandblasting the Parker Solar Probe spacecraft in all kinds of interesting and less exciting ways. But we can actually detect the impact rate based on voltage potential spikes from the Fields instrument. And there's a long history of detecting impact rates due to these electric field observations. And one of the advantages is that you get the entire surface of the spacecraft is now a collecting area. And one of the disadvantages is that it's not a calibrated dust detector. And so you don't know exactly the mass and the speed that's hitting you, and the directionality is also very difficult. But raw impact rate, you can do very well. And actually, there's very recent work by Mitchell Shen at University of Colorado Boulder that is really opening the door, Mitchell Shen and colleagues, that's opening the door to try to crack open that speed and mass dependence by understanding the waveform shapes and comparing it to lab results. And that's very exciting. We might be able to turn this data set into a more calibrated data set. So the impact rates that we got now are shown here on the right with Parker Solar Probe. And the white dots are the data. And what we did is this is from the first analysis, we tried to fit it with two different populations separately. We first tried with just the zodiacal cloud, which is the cloud of grains that are bound. There's all these Jupiter family comets, asteroidal, Halley type comets, everything that comprises the zodiacal cloud. We assume, in a first approximation, they're all in perfectly circular orbits, and they have a density that scales like the Helios observations, r to the minus 1.3. And so that's what's shown in these two different green curves, two different representations of that model. And actually, that model did a pretty poor job of reproducing the impact rates. And so then we asked, okay, what if it were the collisional byproducts? So these bound grains that very slowly, not as exaggerated as shown here in this cartoon on the left, spiral into the inner solar system. They collide because it's denser there. The collision rate is higher. And when you fragment a grain small enough, it turns out that radiation pressure, the pressure from light, actually can blow that grain out of the solar system. It can overcome gravity, and you can become an unbound grain on a hyperbolic trajectory. And those are called beta meteoroids after the parameter beta, which is the ratio of radiation pressure to gravity. And so in even a very, very simple model where we just assume betas are produced at one single location and they all have the same beta value. We tried 3 here, 0.5, which is the smallest you can get in this setup, 0.7 and 1.2, and those are what those purple curves show. It turned out that beta values in the 0.7-ish range reproduce the data remarkably well. And so Parker is actually, at the first few orbits, it was measuring a large flux of beta meteoroids. And those beta meteoroids actually are in number flux, the largest number flux population at 1 AU of dust in the interplanetary environment. And so we asked the question, well, we spent all this time trying to understand, well, how could there be more material coming from the sun than going towards the sun if it's all bound? And so then asked the question, okay, well, here's an asymmetry. Here's a broken symmetry. There are beta meteoroids. They only go one direction. They only leave the solar system, and they come from the sun. And so then we applied a simple model to ask, well, where do those hit the moon and at what speeds? And so here shown on the left in the top panel is the impact speed as a function of that beta parameter for reasonable range. And then each curve is starting at those beta meteoroids at different radii from the sun. For example, 5 solar radii, we think that's about the closest they get before they can't really start much interior to that. That's probably a sublimation zone that grains can't exist. And 10, 15, 20, 30. Recent analysis seems to suggest maybe the majority are produced in 10 to 20 solar radii in a more recent paper. And so you can see that the impact speeds at the moon are anywhere from 50 to almost 150 or more kilometers per sec. Very much larger impact speeds than the sporadic background that are somewhere in the 10 to 60 kilometers per sec. The second panel on the left shows the direction, the location on the moon where they hit in local time, where 12 is noon, that's the subsolar point, 6 is dawn, that's that terminator. And you can see that even over a wide range of parameters, they impact at about 1030 to 1130. And I've marked where the helium source is on here too, and this is a compressed y-axis, but they impact the moon very similar locations to the helium source. And so the last piece was, well, can these tiny little grains, and they're in the range of 100 to 300 nanometers in radius. And so the biggest grains are actually on the smaller end of the ejecta we can even detect. And so then it's a question of, well, can impacts even at those high speeds generate sufficient impact ejecta mass for us to even measure it? And so that's what's shown here on the right. And the x-axis is now the ejecta yield, which is the ratio of ejecta mass to impactor. So if you have a 1 gram impactor and a yield of 10, then you produce 10 grams of ejecta, and that's what the yield of 10 means. And on the top shows the grain size impacting, and the beta meteoroids are shown in this band. And so the main thrust of this is, and here's our two thresholds of 0.3, 0.7 for the detector. And what we found out is that in order to detect these grains, we would need a detection threshold of something, or a yield of something anywhere in the 10s to 10 to the 4, which is a very large range, but it's actually well within the reasonable range of what we observed at Galileo. And so it's possible that beta meteoroids could produce large enough and sufficient enough grains to detect. And so then when we put that source in, that asymmetric from the sun source that's shown on the bottom left, and we add it to a more symmetric model of the helion and anti-helion, that's this, so now it's on the bottom, the second little moon image, and you add those two together, you get this asymmetric impact ejecta cloud that seems to mimic pretty well, qualitatively at least, the observations from LDEX. And so we've kind of coalesced onto this view of the lunar ejecta cloud, where there might be an intrinsic asymmetry that's due to collisions that happen very near to the sun, and they're constantly sandblasting the sunlit side with these outbound trajectories. They didn't quite make it out of the solar system. They get stopped by the moon. Oh well. And so the main story here is that in the equatorial region, probably these 5 sources are mainly responsible for creating this structure that we observed. So that was a summary of kind of our understanding to date of the LDEX measurements, and Wing had asked me to focus and discuss possible future observations and where we could go from here. So the rest of the talk is kind of a more hopeful and discussion on where we might be able to make more progress with more missions and more studies. And so to do that, one of the really scientifically exciting regions of the moon there's more exploration to do is the polar regions. And so we can try to extend this knowledge that we've gotten from LADI to the polar regions and make predictions, but in the end, what we really need to do is go there and learn about it with a spacecraft and a polar orbiter equipped with the instrumentation adequate to answer the science questions that are still unresolved. So this is a schematic showing kind of the overview of volatile transport, that being water or other volatiles in the lunar polar regions. And there are regions where the sun does not shine on any surface for any amount of time, and so you can get sequestered volatiles that then get stuck and adhere to the surface and can potentially stay there for a long time until an impactor comes and liberates it and produces impact ejecta and dust and gas, and it reblankets the surface. There's volatile losses. And so while the sun cannot access some of these craters in the north and south pole, the northern and southern toroidal meteor sources and meteoroid showers can access these. They're not blind to that. And so those physical processes, there's some interesting interplay between solar phenomena and meteoroid activity in the polar regions. So before, I'd just like to mention that there was a very interesting study that came out about 2 years ago by the neutral mass spectrometer team. And what they showed was that during the times that their neutral mass spectrometer was actually off, they would collect water in it. And then every time they would turn on, they would get this enhanced water signal. And they use that as kind of a statistical measurement over a longer time scale to say, well, how much water hit the spacecraft in that amount of time we were off. And when they did a lot of data analysis to reduce that down into kind of a comparable impact rate that's shown here on the left, those rates correlated very well with many of the meteoroid streams. And that's because these meteoroid streams could potentially access regions in the lunar soil that had sufficient water to then, and once water is released, it goes in these large ballistic trajectories, and it's kind of a very global measurement that NMS is able to make. And they found, their conclusion is that in the equatorial region, they did not see kind of a persistent level of water. They saw it only during the meteoroid streams. And the meteoroid streams are on average a bit sometimes faster and certainly larger impactors on average than the sporadics. And so their conclusion is that in the equatorial region, there's this desiccated water deficient layer that's maybe about 8 centimeters deep. And if a grain can, or if a meteoroid can impact and produce enough shockwave and to get to the water-rich layer underneath, rich being kind of a relative term, then it can release water. And so their result was that there is in the equatorial region this desiccated layer, and we don't know how that desiccated layer might change as a function of altitude. And so that's an unknown. Is that kind of more water-rich layer? One, is this accurate? And two, if it is, how does this desiccated layer vary as a function of latitude? Because Lati was in an equatorial orbit. But what we do know about the polar regions is there is evidence for water in the permanently shadowed regions. So this is by an excellent paper by Paul Hayne and colleagues that shows the signatures of water and the maximum temperature. And you can see these dark regions are places where the sun can't heat up the surface for any amount of time. And for some of them, but not all of them, there was signatures of anywhere between 0.1 and 2% water by mass in these cratered regions. And this is a huge potential resource that has been a big focus of human exploration, because if we can send humans to the moon and they have a way of gathering water in some way, then they don't have to carry it with them, and it saves cost and weight and could enable moon bases on a more rapid timescale. And additionally, the 0.1 to 2% might be conservative. It might be up to 10% if it's a more kind of uniform water layer. And so we do know there is water that gets sequestered in some, but not all, of the permanently shadowed regions. And so kind of why that is an ongoing mystery. And understanding the interplay between meteoroid bombardment and these regions is crucial to understanding this. So there was a study recently by Peter Pokorny and colleagues that showed what I just mentioned, how there's a northern untoroidal source. So this is the impact speed as a function of latitude. And you can see here that most of it is peaked in the colors mass flux per day. And then on the right is kind of an integral over speed. And you can see there's two bumps there in each hemisphere. There's one kind of near the equator at 20-ish degrees, plus or minus. And then there's another bump at 60. And that is the northern and toroidal sources that can freely access these shaded regions where the sun cannot, and they can liberate impact ejecta. And by another recent study by Bill Farrell and colleagues, they found that we looked at what are the consequences of the interplay between sublimation and solar wind and impacts to these permanently shadowed regions. And what we found was that if the surface temperature is below 104 Kelvin, for example, in this setup, that sublimation is actually the less dominant process in causing water to lose, because it's so cold that the surface can hold on to that water much longer. But impacts are actually then the non-thermal processes, impact ejecta, impact vaporization, and then solar wind sputtering, are the dominant loss processes for emitting water at these permanently shadowed regions. And so there's but we've not yet to observe this, and so this is an excellent first step in understanding this water cycle at the moon. And so another study even more recently by Pokorny et al. Last year, now on the right shows, this is the top right is the meteoroid flux to the South Pole, and then the bottom is the amount of impact production. And kind of what I point out, there's these three craters, the 1, 2, 3, and the kind of top right, quadrant 1. And they get kind of comparable amounts of impact ejecta production. And yet on the left in Paul Hayne's figure, you can see that these three different craters have a significant amount of heterogeneity. They have a lot of different varying amounts of water in these three craters. And so clearly, this is not the end of the story. It's not as simple as the amount of access that meteoroids have, and there's more to the story. But this is a very important driver in understanding those drivers. For example, if we were to fly over all three of these craters and measure exactly what is the outgoing water rate and the incoming meteoroid flux, would be critical to understanding some of these mysteries on the water evolution at the moon. So to do that, we've made some initial predictions on what we might expect, and the end goal being to send a dust detector and a neutral mass spectrometer to those polar regions and directly measure what's going on. So for example, on the left here is a kind of a more toy model again of the meteoroid environment at the moon. You can see the helium and anti-helium source that come from the roughly solar anti-solar direction. There's an apex source, and then the northern and southern toroidal, which are the dominant impactor populations in the polar regions. We add them all together with the appropriate ratios, and that's what that big map shows. And then on the right shows the ejecta flux coming off the surface of the moon as a function of latitude. And you can see the kind of the curve with the most variation at 0 degrees latitude shows that grade 8 symmetry that we saw with LDEX, and it was informed by the LDEX measurements. And that's peaks at dawn, and it's a minimum near dusk. And then as you work your way up in latitude, the longitudinal dependence or local time dependence actually kind of winds down because you're kind of more dominated by a source that's directly impacting that region, and so you get actually less local time variations in the flux. And so we can take that and make expectations for what a polar orbiting spacecraft would observe. And again, this is actually not taking into account that extra fun hyperbolic source that we talked about, but which would make an asymmetric part to the sunlit side. But with that symmetric model that I talked about, the one I just showed, you can see here now for a polar orbiter, the top panel is a side view now, not the top-down view of the lunar dust cloud, what our expectations are. And these are for various different cuts, the 6 to 18 local time, the 9 to 21 local time, and then the noon to midnight local time. And so this gives us at least some context on what we might expect. And the main takeaway from this study was that the polar region is actually not devoid of impact ejecta. There's no reason to believe it should be. We think that it actually has, in some places, more ejecta than its comparable equatorial region. And so you can see that kind of dashed dotted line. That's the noon to midnight orbit, and you get densities and fluxes that are very similar to what we measured in the equatorial orbit. So if we were to go there with a dust detector, we absolutely expect to measure appreciable and get great statistics on the impact environment. And to be even a little more ambitious, it's conceivable. So we would want a neutral mass spectrometer also to measure the volatile environment at those polar regions. That would be an excellent, huge measurement. But there is also some interesting compositional information that's locked in those dust grains. The dust grains themselves are carriers. They are imprinted with the information of the composition of the surface that they just got kicked out of, and they're dense information carriers compositionally. The problem is that at impact speeds at the moon, it's very difficult to do compositional analysis because you need large impact speeds and then energies to break apart those grains into molecules and atoms to do mass spectrometry. But we have maybe an initial idea and thought that if there are water groups on the surface of the grains, that it's possible due to like van der Waals forces and some other interesting chemical processes, there might be some cleavages that allow you to separate just the water, there's the superficial water constituents, and they might generate ions in a mass spectrometer, and we might be able to then measure water content with a dust detector of the dust grains, where we know we'll get great statistics. So we take all that, and the next really exciting thing to do, certainly with a dust detector at the moon, is then send it on a polar orbit. And we know that lunar volatiles are efficiently liberated. And so the cross comparison between the volatile environment and the dust environment, because we get now the impacting fluxes down that kick up the volatiles, we can measure both the influx down, the upgoing ejecta, the upgoing volatiles, and put it all together in a nice story that we just simply don't have the measurements for right now. On the left here, the gray line shows the average impact rate during the Geminids meteoroid stream, the most intense thing that generated impact ejecta at the moon while we were there. Then the white shows the measurement remote column density of potassium measured by the third instrument, ultraviolet spectrometer. And then these various colored curves show the decay time from the input in gray to the output in white. And we were able to use the combination of the volatile observation with the impacting dust flux to determine that there was a decay constant of about 4 to 8 days of at least potassium on the moon in its lifetime. And so this was a constant you just really couldn't get any other way, because if you model it, it's a combination of many model parameters, but you get the ground truth when you measure it in situ. And so to do this for a bunch of different elements live and in the polar environment would just be a profound addition to our understanding of the polar region. And so shown here on the right is kind of a schematic showing where we've done some predictions for what a mission would be like. And we would be able to swing around the night side and the sunlit side in this polar orbit, and we get great ejecta measurements. And you can see here this northern and toroidal source that we put in, and that's what's generating a lot of the ejecta we would expect. So last, that was kind of the end of the lunar discussion. I just had a couple slides that I wanted to portray how we can extend everything we've learned at the moon now to other airless bodies throughout the solar system in two different really exciting ways. One, what we've learned at the moon and at the icy moons of Jupiter is that every single airless body seems to at least have a yield over 1, which means that you get an impactor that kicks out more mass than what went in, which means that all these airless bodies are amplifiers. And so if you go and fly by them, you get an amplification of the dust environment that they are in. And so if you want to understand that dust environment, where there's a lot we don't understand past 1 AU, where we don't have complex radar measurements. For example, at Mars, we don't have radar measurements. We don't know what the meteor shower environment is Mars, but if we were to use, say, Phobos and Deimos to be amplifiers of their environment and fly by them a bunch of times with dust detectors, maybe we could get a handle on the meteoroid environment at the moon, and if astronauts are there, they would know when to hide when it's going to rain rocks. And so that's a kind of an engineering application, but also a scientific application in terms of understanding the cometary environment in the solar system. We also could do flybys of these other bodies, and if we had composition capability on the dust detector, because they're an amplifier, there's a bunch of their material that's just constantly surrounding them, just waiting to be scooped up and analyzed, and then you don't have to land on the body itself. You actually just need to fly by it with a compositional dust analyzer, and then you can actually kind of taste the asteroid without having to spend the delta V to land on that. And so, for example, we could take the lunar cloud that we know and have well analyzed. That was an exponential altitude. We can apply the exact same speed distribution to a small asteroid, where then the density distribution will scale like Coulomb's law, essentially assume gravity is negligible in that approximation. And so on the right is this lily pad kind of structure, and that's what we would expect the impact ejecta cloud for asteroids on circular orbits to look like. And we could then fly by them, like I just described. And so here is showing a bunch of different flyby geometries, and even by one single profile, you would get the composition of the asteroid you flew by, and you would get, it's almost like a Langmuir sweep, you would get the kind of the relative competition of the various impactor sources in some other region other than 1 AU in a very unique way that you just couldn't do without that amplifier that is the airless body. And another one of the big questions that we just don't know now is, well, what is the impact yield of asteroids? And asteroids have a variety of different regolith sizes and compositions, and they are constantly shedding material into the interplanetary complex. And so how much they're shedding is a function of this ratio of the yield, the ejecta mass to impactor mass. And probably, so the moon is probably something like 10 on average, and the icy moons that are more efficient at liberating, they're probably in the 1,000 to 10,000 range. Asteroids are probably somewhere in between, but we just don't know. And so there's some basic fundamental impact physics that we don't yet understand, and even one asteroid flyby would push that forward immensely. So there are at least three upcoming missions with dust detectors that are very exciting. There is Density Plus. It's a Japanese mission with a German dust detector that's going to fly by an asteroid with composition capability. That's the parent of the Geminid stream, and that launches in 2022. There's IMAP that launches early 2025 that has a very large dust detector with compositional analysis. Very exciting. It's going to measure interstellar material flowing into our solar system, as well as the cometary material at sizes smaller than we can measure with radar. And so there's below, say, 10 microns, we just can't really measure the population of grains, which are more abundant, and this one will be able to do that. And finally, Europa Clipper will fly by Ganymede with compositional analysis, and it might even be able to detect traces of amino acids if they exist at Europa, and so that's very exciting. So in summary, the Ejecta cloud at the moon, we've now kind of have a comprehensive picture that we think is physically motivated, that it's sustained by a bunch of different interplanetary meteoroid sources. All airless bodies are efficient amplifiers of their local meteoroid environments. The impact ejecta environment of the polar region specifically has just not yet been explored and characterized, and there's a lot of critical science and engineering aspects to understand by sending a polar orbiter with the appropriate instrumentation to characterize this and really figure out what's the meteoroid, what role does meteoroid bombardment play. It's likely a very critical role in the total volatile life cycle at the moon. So with that, this is my last slide. I just wanted to end with some open questions and future measurements. So what is the impact? We don't just fundamentally, what is the impact ejecta environment in the polar regions? Right now we do not have a measurement of that. What processes drive volatile evolution in these regions, and what role do meteoroids play in that? What is the impact yield for impacts into surfaces? It's still fundamental physics we don't fully understand, and does it vary for asteroids, and why? Do beta meteoroids play an important role in space weathering? This was the most physical source we could come up with. It's by no means a proof, but until we have a better idea, this is what we're going with. And then future measurements, some of which are not yet slated. So we should definitely have a polar impact ejecta observation that includes permanently shadowed regions. We could get the ejecta flux, the yield, gardening, composition with some caveats as I described. Like to get the flux of interplanetary meteoroids at 1 AU and to the lunar surface with small impactors. That'll be done by IMAP, which is very exciting. And the beta meteoroid flux, which maybe could be done on the surface of the moon. And finally, characterizing asteroid compositions, multiple of them, by flying by them and just sampling this opportunity nature has provided us with all this material surrounding the asteroids, and scoop it up and analyze it. And that'll be done with Destiny Plus, at least for one asteroid. So with that, I'm happy to take questions, and thank you.
Yeah, thank you so much, Jamey, for this very interesting talk, really. And anyone in the audience want to ask Jamey a question now? Can unmute yourself and ask the question, please. Before anyone have the question, I would like to ask Jamey one or two questions first. I find it, I mean, what is the basic reason that the lunar dust distribution and the icy moon's dust distribution from Galileo, one has power law distribution, one has exponential law distribution?
Yeah, so I think that they might be two sides of the same coin. So the Galileo measurements were all at least one lunar radii, one moon radii, satellite radii, away from that satellite. And so they were measuring kind of in a regime where you would expect probably to be dominated more by, the faster grains that were able to escape and get to that region. They might not have just been able to probe the smaller speed region than LADI probed because we were so low in altitude. And the assumptions that they made to understand, which were totally reasonable, those density distributions, were that the ejecta speed is a power law, which has a cutoff. And we know that can't be true. We know that there will be grains that have smaller speeds that do exist. And so I think what LADI has been able to do is maybe fill in that gap and show how there is actually a very reasonable way that nature has figured out how to distribute speeds into the lower speed ejecta region. So that my guess is that we were just probing, we were always below a planetary radii and they were always above, and we're probing different physics.
Okay, so and because you have done a lot of work on the simulation on the polar dust cloud distribution, I think. So what kind of velocity distribution you use, in your model?
So with lack of anything better, we use the same one, and we do use for these various sources, we use what their appropriate average speeds are. So for example, helion and apex and antihelion, we use, I think it was 11 kilometers per second. By average, I mean average in terms of mass production, because mass production goes like speed to the 2.4 something, and so we take the average, the integral of the v to the 2.4 moment of the speed distribution is 11 kilometers per sec for these guys. It's 60 for the apex. It's 13, I think, for the northern and southern toroidal, or maybe I'm not remembering that one right, but they have a bunch of different speed distributions, and we do account for that appropriately to build this ejecta environment.
Yeah, and you mentioned about the polar orbiting measurements. What is the prospect, from the NASA side? Have you been proposing for it?
Yeah, so we tried with KPLO, the Korean orbiter. Right now, to my knowledge, there's not a proposal in, but with this Artemis push, there's a lot of future lunar missions that are in support of both science and putting humans back on the moon. And so, it's conceivable that there will be more opportunities. I think this is a really important, and the same reason that LADEE was born, one of the reasons LADEE was born is that there was this big push for lunar exploration, and it's almost like going to the wildlife before you start putting in some buildings and understanding the ecosystem before you get there. And so that was LADEE's purpose in the equatorial region, but at the polar region, we kind of would like to maybe make those measurements before we go there and modify it in some appreciable extent with a bunch of rocket landings and say human exploration and rovers on the ground. And so that's another big reason why we should have a polar orbiter soon.
Yeah, well, we should not discuss here, but then I did talk to Szalay, when he gave the talk on the Dusk, and he, of course, he's very fond of this measurement in the polar orbiting, spacecraft, and so I would say that the next time you go to Boulder, just find Sean and Szalay, talk to them and say whether they ask Sean to have enough courage to stick in a proposal to Taiwan. I think that we'll be very happy to work with with you guys on I think especially if you talk about the Artemis mission.
Is Taiwan planning to put polar orbiters?
Well, we originally have a polar orbiting mission, but now that they have to reevaluate, because it's not so easy. On our hand, if they really do go ahead, I think to have a very good scientific objectives, and I would say that easy to understand, not easy to understand, but just basically people can see what that is, and have it's very interdisciplinary, and then it has a very specific goal, in probing the volatile storage and transport mechanism. Yeah. And so you don't need that to have mountains of lunar science to do the experiment. That's what I meant. Yeah. So I think that would be a very, very an experiment of high potential. Then in whichever way, I think that we should be happy to to pay more attention to that. Yeah. Any other questions from the audience? It's the time to ask. The Jamey touched on a number of things, and in particular, I don't know how I mean, is that your idea? Going to Phobos to have a dust storm warning system for the astronauts.
Yeah, they're amplifiers, and you couldn't orbit Phobos and get dust measurements because the escape speeds are so low. But if you orbited Mars and flew by Phobos a bunch of times, you could get some statistical understanding of the meteoroid environment using that planetary body that nature has already put there as an amplifier and a tool. And that meteoroid environment is not well constrained. We don't have radar systems at Mars.
Well, I just also want to mention that because you talk about the asteroid, this measurement nearby asteroid, of course, destiny would be the next opportunity. But I don't know whether you know that there's a Chinese asteroid mission. In fact, they will be orbiting around, and one on a small asteroid. And afterward, they pick up some sample and return it to the Earth, and then the spacecraft will swing by and go onto an active asteroid.
Oh wow! Great.
And they have, from what I heard, they do have a it does detector.
Huh.
Yeah, on board. The dust detector is the function is kind of similar to the guider on Ejector, but presumably have a higher capability. You know, so I haven't seen anything from experimental description from them yet. But I think that maybe there's something that would be interested in knowing more. Yeah.
That's exciting.
Okay, good. Any other questions from the audience? If not, and I would let Jamey go because it's pretty late. How late did you sleep in ordinary?
No, it's before my bedtime still.
Before your bedtime, you still 3 hours to go.
Yeah, an hour maybe. So
an hour.
No problem. Yeah.
So maybe I should ask you to give another talk. Okay, Jamey, thank you so much. And then there's still some other questions that I will write to you, right? Including writing to David and spend another hour, wisely and write another paper. Okay, thank you so much. Good night. Yeah.
Thank you, Ing. Very good to see you. Thank you.
All right.